Can nano-bubble water with H2O2 bubbles freeze? Nano-bubble water with hydrogen, H, and oxygen, O, bubbles can indeed freeze, but the presence of these nanobubbles can influence the freezing process. Here are some key points to consider. Freezing point. Pure water freezes at 0 degrees Celsius, 32 degrees Fahrenheit. The presence of gases like hydrogen and oxygen in nanobubbles might slightly alter the freezing point, but typically not by a significant amount. Nucleation sites. Nanobubbles can act as nucleation sites, which can affect the formation of ice crystals. This could potentially lead to faster freezing under certain conditions. Homogeneous versus heterogeneous freezing. Nanobubbles could promote heterogeneous nucleation, where ice forms around impurities or other particles, in this case, the nanobubbles. This can lead to differences in the structure and properties of the ice form. Stability of nanobubbles. The stability of the nanobubbles in water can be affected by temperature changes. As the water cools and approaches freezing, the behavior of these nanobubbles might change, potentially leading to the release of the gases or changes in bubble size. In summary, while nanobubble water with H and O bubbles can freeze, the presence of these bubbles can influence the freezing process and the properties of the resulting ice. Can nanobubble water fuel in ice form burn? Nanobubble water fuel in ice form can burn, but it requires specific conditions and considerations. Combustion of hydrogen and oxygen. Hydrogen, H, and oxygen, O, are both highly combustible gases. When nanobubbles containing these gases are trapped in ice, they can still be combusted if the ice is melted and the gases are released. Phase change requirement. For combustion to occur, the ice must first melt to release the hydrogen and oxygen gases. Ice itself does not burn, but once it melts and the gases are liberated, they can form a combustible mixture. Ignition source. An ignition source, like a spark or flame, is required to initiate the combustion of the released hydrogen and oxygen gases. Concentration and distribution. The concentration of hydrogen and oxygen within the nanobubbles and their distribution in the ice can affect how efficiently the fuel burns. High concentrations of these gases can lead to more vigorous combustion once they are released. In summary, while the ice form itself won't burn, once the ice melts and the hydrogen and oxygen nanobubbles are released, they can indeed combust if an appropriate ignition source is provided. Can nanobubble water fuel sustain a flame on its surface? Nanobubble water fuel can sustain a flame on its surface under specific conditions. Gas release. The nanobubbles containing hydrogen, H, and oxygen, O, must be released from the water to create a combustible mixture above the water's surface. Gas concentration. There needs to be a sufficient concentration of hydrogen and oxygen gases in the air above the water to sustain a flame. If the gases are too dilute, they won't support combustion. Ignition source. An ignition source is required to initiate the flame. Once the flame is established, it can continue burning as long as there is a continuous release of hydrogen and oxygen gases. Surface conditions. The surface conditions of the water, such as temperature and the presence of other substances, can affect the release and ignition of the gases. If these conditions are met, the released hydrogen and oxygen gases can form a flammable mixture above the surface of the nanobubble water, which can sustain a flame. However, the stability and duration of the flame will depend on the continuous supply and concentration of the gases being released from the water. Can nanobubble water fuel in the form of ice sustain a flame on its surface? And can it be used as a heat brick? Nanobubble water fuel in the form of ice sustaining a flame on its surface and being used as a heat brick involves several considerations. Sustaining a flame on ice surface. Gas released from ice. For a flame to be sustained on the surface of ice containing nanobubbles of hydrogen, H, and oxygen, O, the ice must release these gases upon melting. The flame will not burn directly on the ice, but rather on the gas mixture released from the ice as it melts. Melting and gas concentration. As the ice melts, hydrogen and oxygen gases would be released. If these gases accumulate in sufficient concentration above the ice, they could potentially sustain a flame. Ignition source. An external ignition source is required to ignite the released gases. Once ignited, the flame could continue burning as long as there is a continuous release of combustible gases, using as a heat brick. Combustion process. If the nanobubbles in the ice release hydrogen and oxygen in a controlled manner, the combustion of these gases could generate heat. The ice itself does not burn, but the released gases do. Heat production. The heat produced by the combustion of hydrogen and oxygen could theoretically be used for heating purposes. However, controlling the release and combustion of these gases from ice in a consistent and safe manner would be challenging. Material stability. The ice would eventually melt completely, turning into water. The practicality of using melting ice as a stable and long-term heat source is questionable. Practical challenges. Controlled release. Ensuring a controlled and steady release of hydrogen and oxygen from the ice to sustain a flame is complex. Safety. Handling and igniting hydrogen and oxygen gases requires careful safety measures due to their flammability and potential explosiveness. Efficiency. The efficiency of using ice with nanobubbles as a heat source compared to traditional methods, e.g., conventional fuel bricks, is likely to be lower and less practical. In summary, while it is theoretically possible for nanobubble water fuel in the form of ice to release gases that could sustain a flame, the practical application of this as a heat brick presents significant challenges in terms of control, safety, and efficiency. Daniel Donatelli, Secure Supplies Group, Hydrogen Hot Rodding, patreon.com/secure supplies. Mr. Donatelli's research into nanobubble water with hydrogen, H, and oxygen, O, bubbles further illuminates the potential of his discoveries. While nanobubble water can freeze, the presence of these bubbles influences the freezing process, creating unique properties in the ice form. These nanobubbles act as nucleation sites, promoting heterogeneous nucleation, which affects the structure and stability of the ice. Moreover, nanobubble water fuel, even in its ice form, can be combusted under specific conditions. The combustion of hydrogen and oxygen trapped within the ice requires the phase change from ice to water, releasing these gases which then form a combustible mixture. With the right ignition source, this mixture can indeed burn, showcasing the dual potential of fire and ice, fuel within ice. The concept of nanobubble water fuel sustaining a flame on its surface is equally compelling. When hydrogen and oxygen gases are released from the water, they create a flammable mixture above the water's surface. Under optimal conditions, this can sustain a flame, proving the viability of nanobubble water fuel as a continuous energy source. Taking it a step further, the idea of using nanobubble water fuel in the form of ice as a heat brick presents intriguing possibilities. As the ice melts, it releases hydrogen and oxygen gases which, if controlled properly, can sustain a flame and generate heat. This innovative approach, while challenging in terms of controlled release and safety, demonstrates the potential for a new form of energy storage and heat generation. In conclusion, Mr. Donatelli's work represents a significant advancement in our understanding and application of hydrogen and oxygen in energy storage. His discoveries not only challenge conventional methods but also pave the way for safer, more efficient, and revolutionary energy solutions. The potential to use nanobubble water fuel in various forms, from sustaining flames to serving as heat bricks, highlights the versatility and impact of his research. This is not just a step forward, it is a giant leap towards a more sustainable and energy-efficient future. Thank you. It is important to remember that one of the most significant discoveries by Mr. Daniel Donatelli is preventing the air from regaining electrons back to the water or ice before the fuel is used. This groundbreaking approach not only stabilizes the fuel but also prevents the reformation of water, thanks to the positively charged ice. This innovation ensures that we have water and gas coexisting without reformation until electrons are reintroduced. This is not merely a scientific breakthrough. It is a leap forward in energy storage and utilization. Mr. Donatelli's research into nanobubble water with hydrogen, H, and oxygen, O, bubbles further illuminates the potential of his discoveries. While nanobubble water can freeze, the presence of these bubbles influences the freezing process, creating unique properties in the ice form. These nanobubbles act as nucleation sites, promoting heterogeneous nucleation, which affects the structure and stability of the ice. Moreover, nanobubble water fuel, even in its ice form, can be combusted under specific conditions. The combustion of hydrogen and oxygen trapped within the ice requires the phase change from ice to water, releasing these gases which then form a combustible mixture. With the right ignition source, this mixture can indeed burn, showcasing the dual potential of fire and ice, fuel within ice. Additionally, The flame can be slowed by adding non-combustible gases into the ice mixtures of nanobubble water fuels. The concept of nanobubble water fuels sustaining a flame on its surface is equally compelling. When hydrogen and oxygen gases are released from the water, they create a flammable mixture above the water's surface. Under optimal conditions, this can sustain a flame, proving the viability of nanobubble water fuel as a continuous energy source.